Okay, let's finish up lecture notes 3. This is going to be examples of 3 techniques. We're now going to start with the example the book uses most often, which is student-teacher ratios versus test scores. So they give us a plot of student-teacher ratios on the x-axis versus test scores. And so we're supposed to find whether or not there's a relationship between these two variables. They've given us a scatter plot. What does this figure show? Is there correlation between these two things? It's hard to tell from this scatter plot. Maybe you could imagine drawing a line that has a negative slope through here, but really this is kind of a mess. It's hard to see anything from this. So do we have any tools that can help us so far? So the question is student-teacher ratio correlated with test scores, and what are some ways to test this? Alright, the null hypothesis. Let's say we can divide up classes into small and large. And the null hypothesis is that the class size has no effect on student achievement, or there's no correlation between class size and student achievement. So we can write our null hypothesis as the average outcome, or the average score, y bar, for the small class sizes, that's this thing here, minus the average score for the large classes. The difference is equal to 0. So if there's no difference, that means the large and small classes have no relationship to test scores. So we're given a data set of small and large classes with average scores of 657.4 for the small classes and 650 for the large. And we're also given standard errors of these estimates, and then the number of classes we sampled in each. So we sampled 238 small classes and 182 large classes, and then we took the average test scores in over each of those samples. Okay, the first thing we can do is just an estimation of the difference in means. So what we're doing is we're taking the average of the test scores of the small minus the average of the test scores of the large. So we're doing y bar small minus y bar, oops, I already wrote this over to the left, y bar large. And then we're taking these and plugging in their definitions. So y bar small is 1 over n small of the sum of I equals 1 to n small times yi. And then y bar large is 1 over n large times the sum of I equals 1 to n large times yi. From the previous table, they just gave us these values, 657.4 and 650. So we subtract them and we get a difference of 7.4. Great. So you could go, if you're tasked, if you're a consultant, and you're tasked with figuring out do class sizes affect average test scores, you could take this back to your boss and say, look, smaller classes have 7.4 higher scores on average than large classes. So the boss would then look at you and say, so what does that mean? Is 7.4 large? Is that a large difference? Is it big enough to is it a big enough difference to warrant school reform discussions? Should they put some money into this? Is it statistically significant, or is it just random sampling error? Okay, so we can do some hypothesis testing. We can construct a t-statistic for the difference in the two means. A t-statistic for the difference in means is just going to look as follows. So we're going to have the t value, or the t-stat, equal to the difference of y bar small minus y bar large minus 0. We left out the minus 0 because that's our null hypothesis. We could put the minus 0 just to be complete, but it would drop out. And then we're going to divide by the standard error of the difference of the two. So this thing, the formula for this is on the right here. So it's going to be y bar small minus y bar large over, this turns out to be the formula for the standard error of a difference. And we can plug in values. So we know what the standard error is for the large and the small. so we plug in those values here, and we just do all this math, and we get 7.4 over 1.83, which is equal to 4.05. So remember our rejection rule for our t-stat. If the t-stat in absolute value is greater than 1.96, we can reject with 95% confidence or the 5% significance level. Is this t-stat greater than 1.96? Yes, it is. So we can reject with 95% confidence. Let's do a 95% confidence interval for our difference in means, assuming the null is true. So remember the 95% confidence interval is just taking the difference plus or minus 1.96 times the standard error of the difference. So 7.4 plus or minus 1.96 times 1.83. So our 95% confidence interval is 3.8 to 11. That means that we can't reject anything in that interval as being the true difference, assuming the null is true. So two equivalent statements. 95% confidence interval for difference in means does not include 0, so we can reject the null hypothesis again. The null hypothesis that the difference is equal to 0 can be rejected at the 5% significance level. A p-value, remember, this is going to tell us how confident we can be. So the p-value formula is just when we don't know sigma squared, we're going to use the standard error of y bar, or this sampling distribution of y bar. So then we just end up with the t-stat. So it's the negative of the absolute value of the t-stat. So we plug that into here. Go look it up on the z-table, multiply by 2. Turns out negative 4.05 isn't even on a z-table. It's so far off. So we're extremely confident. So this is essentially saying we're 99.999% confident. There's a very low probability of getting a difference in means further from the null, supposing the null is true, if we drew another sample of classes and estimated the difference in test scores.